Hello all, welcome to this lecture on elements of mechanical engineering, where we are in the third module. My name is Atchuta Ramacharyulu and I am working as an assistant professor in the Department of Mechanical Engineering. Now in this lecture, we are going to study the mechanical properties of metals. So, in the previous lectures, we have seen there are different types of metals like ferrous metals, non-ferrous metals, and some other non-metals also there like glass, rubber, etc. So, when we study engineering materials, we should know some properties. There are some basic properties upon which each material can be used. A metal or a non-metal can be used depending on its property. Each and every metal will have different property. Now, we are going to study all these properties by using which we can identify or we can use a particular metal. So, depending on their particular property, a particular metal can be selected. So, in those, the first property is strength. So, what is strength? So, when we study the basic definition of strength, it is the strength of a metal is its ability to withstand various forces to which it is subjected during a test or in service. So, strength is the ability of a metal to withstand loads or forces. And this can be in when the metal is being used in a particular application, or it can be used in a particular service or in testing condition. Okay, it is usually defined as tensile strength, compressive strength, proof stress, shear strength, etc. There are different types of loads that can be applied on a body, yet the body will resist deformation or failure. Okay, so these are the loads: tensile load, compressive load, proof stress, shear strength, etc. These are the different types of loads that can be applied on a body. Even though if the body has more strength property, it will withstand all these kinds of loads. Okay, and then the second property is elasticity. Now, elasticity can be defined as it is the property of a metal when it is perfectly elastic if the whole of the stress produced by load disappears completely on the removal of the load. Okay, now we are going to study this property of elasticity. That means whenever I apply load on a body, I take the example of a metal body and I am applying a load P on it, that is tensile strength, tensile load. So, whenever I apply the load, the body will show some deformation. Okay, upon the removal of this load, if the body gains back its original shape, that means it will regain to its original size, then what it is called? This property is called elastic property. That means the body has more elasticity. So, upon removal of the load, the body will come to its normal position. We can take the example of a rubber band for this. So, when a load is applied on the rubber band, it will elongate. So, whenever the load is removed, it will gains back to its original size and shape. So, this is the best property of most of the metals by which we can design springs. You can see in this picture there is a spring. So, whenever we apply some load on it, it will takes the load, it will bear the load up to some extent, and whenever the load is removed, it will simply gains back to its original shape and size. Not only physically, but when we see atomic level, the metals will have this property of elasticity. They can bear load and they can regain to their original structure. Okay, so if for a metal to have more elastic nature, it should have more Young's modulus. Okay, the modulus of elasticity is proportionally constant between stress and strain. That means we have already discussed the concepts of stress and strain in the previous lecture. Now, there is a relation between these two. Stress versus strain. When we take this ratio is equal to Young's modulus. It is always proportional. So Young's modulus capital E is a proportional T constant that is taken between stress and strain, where we have to compare the relation. When we compare the relation between stress and strain, it is very linear in case of elastic materials. That means we have a graph that is stress strain curve, where we will see the starting line is very straight. That means it is linear. The stress and strain are linear up to this point. After this, it will go down, and after that, it will go like this. So, up to here, from 0 to this point, A, this is called proportionality limit, with which we can design some springs. Like the stress and strain are linearly proportional here. They are varying linearly. So, this indicates the Young's modulus varies linearly within this proportionality limit. So, that is why most of the springs are designed within this limit only. If you want to apply more load, we have to prepare a bigger spring so that it can bear more load, that too within the proportionality limit. Okay, now we'll see another values of Young's modulus. So when we study Young's modulus, it is the property or the ratio of stress to strain. Stress is generally denoted with sigma and strain is denoted with epsilon. So this ratio is called Young's modulus. The values of Young's modulus for different metals is given here. First one is cast iron. The Young's modulus value is 98 like GPa, and wrought iron is 197 GPa, gigapascals, and mild steel is about 210 GPa. All these values are in gigapascals. Aluminum is 72 and copper is 120. So depending on Young's modulus value of each metal, we have to select a particular metal depending on the application. So this Young's modulus is the property of a metal which will indicate how much amount of load it can bear or how much strength it has. Okay, so it is the property of the object or a metal with which we can choose a metal for the particular application. And then next property is plasticity. So plasticity is the property of a metal with which the body will not regain to its original shape and size when the load is removed. So we can see here, if this metal rod, if it is subjected to some kind of load, it will try to elongate, it will try to bear that load by inducing some kind of stress in it, and after the stress has overcome by the load applied, what happens? The body will slightly elongate and we can see the formation of neck. So a small cross-sectional area will be formed. So this is plastic nature. That means once this necking is formed, it cannot be regained to its original cross-section. It is permanent. So this property of not gaining back to its original shape and size is called plasticity. So most of the metals like cast iron and mild steel, beyond the necking formation, will have the property of plasticity. This is no longer elastic in nature. It will not gain back to its original shape. If it get back to its original size and shape, then it is called elastic. When it does not get back to its original shape and size, it is called plastic. Okay, and then we have another property, that is ductility. Ductility is the property of a metal which helps it to be converted into thin wires. You can see in this picture, the metal has been converted into thin wires. Very small cross-sectional area wires can be manufactured. They can be prepared by using the metals which has the property of ductility. So ductility, the example for this ductility is copper. So copper can be converted into very thin wires which can be used in electrical wirings. So this copper can also be converted into thin sheets. Thin sheets also can be prepared which are used in electric devices. So this is also because of the property ductility. That means the definition of ductility goes like this. It is the ability of a metal to withstand elongation or bending. Due to this property, wires are made by drawing out through a hole. So I will do the extrusion process for this. I will take some quantity of metal and I will pull the metal through a small hole so that it will form a very thin wire. Okay, the material shows considerable amount of plasticity during the ductile extension. So whenever the metal is being converted into wires, it will have more plasticity less than elasticity. Okay, so this is another property. And then we have malleability. So malleability, this is a property by which a metal can be hammered or rolled into thin sheets without rupture. Okay, so the best example for the metal having malleability is gold. Gold has a very good malleable property, because of which it can be converted into very small sized objects, and also it can be drawn into very thin sheets. See this. This thin sheet is so thin that it can be cut into pieces with the help of a scissor. Okay, gold is a very malleable property metal, with which, because of this only, the gold can be converted or turned into very small objects with very intricate designs. So because of this malleability property, the gold can be converted into sheets or small objects. They can be hammered or rolled without any rupture. Rupture means without any breakage. We can keep on decreasing the size of the metal. This property generally increases with the increase of temperature. So the malleability will always increases with increase in the temperature. Okay, and then the next property is toughness. So toughness is the strength with which a metal or material opposes rupture. So if I take any metal, if it does not undergo any deformation, or it cannot be ruptured, or any scratches are not being formed due to the application of load, then the body is said to be having high toughness. So when we see this graph, this is the graph, this green color line is for ductile metal, and this one is for brittle metal. Okay, ductile and brittle. So when we compare this area is nothing but the toughness. Okay, so starting from 0 and going up to the failure point at this point, so we can see the property of toughness. The body will not undergo any kind of rupture. This is for ductile metal, and only after this the body will fail. That means a rupture will be seen in the ductile metal. And for brittle metals, this area is very less, only this area, that means only this much of amount it can bear, amount of load it can bear, and beyond which the metal will fail. That means it will be broken into two parts. Okay, this indicates the toughness from the graph. And then we have the brittleness. So what is brittleness? A metal which have very low deformation. When a load is applied, then the metal can be called having the property brittleness. Okay, when a body is very weak, when it is subjected to loads, then it is called brittle. So mostly cast iron is the example taken to explain how brittle metals can be, because a cast iron body or a cast iron plate, when it is dropped on the floor, it will be broken into two parts, just like a brick or a tile. Okay, it is how brittle that is. So cast iron is so brittle that it will not show any kind of deformation. When a load is applied, it will instantly fails. And this is in this photo we can see this is a cast iron metallic rod which is broken into two pieces, where we can see the broken structure of the two parts. Okay, we can actually see there is no deformation. The structure is instantly separated from each other. And then we have another property, hardness. So hardness is usually defined as resistance of material to penetration. Okay, Hard materials resist scratches or being worn out by friction with another body. So in this example, in this picture, we can see there is a tool. This is a tool used for machining. So where do we use these machine tools? So this kind of tool is used to make holes or drill holes on a metal plate. So whenever we are using metal on a metal, what happens if both the metals have the same kind of strength or hardness? We cannot make holes into the plate. That is why we have to increase the hardness of this metal. Okay, the metal which is tool is made up of, so that it can have more hardness and it cannot wear easily. That means it is so strong even when it is made with very small cross section area. It will be very strong. It can be used to drill holes into metal plates. So this is one such type of example where metals have high hardness and they can be used to prepare holes, or they can be used for machining purposes. And then we have the property fatigue. So fatigue is the property. It is observed in the body when a body is subjected to fluctuating or repeated loads. The material will develop a characteristic behavior which is different from that of under steady loads. Okay, so what happens when a body is subjected to repeated loads? Like when we take the example of a continuously moving, continuously revolving turbine. So when the turbine is being subjected to some kind of load which is repeated, we can see the formation of this fatigue zone. If we study this fatigue zone, we can see there is a formation of semicircular cross section here. So what happens when the load is being repeated? That means the load is being positive and negative at the same time. Okay, like if we want to bend or if we want to break a thin wire of metal, we will continuously move in up and down direction. So this will create some kind of repeated load. That means it is being subjected to fatigue. So whenever this fatigue happens, the body will be broken or it will fail at a value very less than its actual strength. So that is why fatigue is a very bad property with which we have to understand that the body should not be loaded cyclically or repeatedly, which will break the body at a very smaller load than the actual weight bearing capacity. And then we have another property, that is creep. So creep is the slow plastic deformation of metal under constant stress or prolonged loading, usually at a high temperature. So whenever we have a body which is working at high temperature, just now we have taken the example of a steam turbine shaft. This is working at a very high temperature because we have a steam that is coming at high temperature from the boiler. So the temperatures are generally high. So what happens when it is working at constant speed, that is at high temperature, the body will tend to fail. Why? Because the rise in the temperature of the body will changes its property. We know the technique forging. So what happens when we do forging? We have to heat the metal and we have to apply some pressure on it in order to change its shape. So the same thing be applied here. When the temperature of the metal is increased and some force is being applied on it, the metal will fail. Simply it will not change its shape. Finally it will break. So this is taken into consideration. The creep is specially taken care while designing IC engines, boilers and turbines. That is where the temperatures are very high and we have to consider the creep also along with other load characteristics. And then we have machinability. So machinability is defined as the ease with which a metal can be machined. A metal can be converted into some kind of shape. The more important criteria for measuring both tool performance and machinability. We have some properties with which we can compare the machinability of a metal. There are like 4 points. The first one is the rate at which the material can be removed. So in engineering tools and machine tools laboratory, we will use these techniques of chipping formation, and where we will remove the extra metal from a metal object in order to create a required shape. So that is where we will use these properties. The first one is how fastly we can remove the metal from a object. And the second one is how smooth and accurate the machining can be done on a body. And third one is the life of cutting tool, or how long the cutting edge cuts satisfactorily before resharpening is required. That means the life of the cutting tool is also taken into consideration while machinability is calculated. And then fourth one is the power required for making the cut. If we want to apply more power, or if we want to use a larger machine which consumes more electricity, so this also has to be considered while calculating the power that is required to making the cut. And we have a formula here, machinability index, which is the ratio of cutting speed of the metal for 20 minutes tool life over cutting speed of standard steel for 20 minutes of tool life. This ratio will help you in finding or calculating the machinability of a particular metal when compared to a standard steel. So we should have a standard steel with which we can compare the machinability of any kind of metal which are used in engineering applications. And then we have weldability. So the metals should have this property of weldability where they can be used to easily be weldable. That means two pieces of same metal can be easily welded together in order to form a permanent joint. So we know the technique welding is used for making permanent joints. It is not a temporary joint because we will heat the two metal plates locally and we will form a joint. Okay, so this joint will be as permanent as the original plates, but yet they can be joined in a very less time. Okay, so the techniques of welding are discussed in the later topics where we will study joining processes. So any material related to engineering, it should have a good weldability. Mostly metals, we don't have this property seen in non-metals. So that is why all these engineering properties or mechanical properties are very important when we study the engineering materials. So that is all for this lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.